Last time we talked about simple interest. I don't think I called it simple interest, but that's what it was. That's where the amount that you're going to get back or the amount that you owe. We didn't really say that. We said if you invest in the bank, it's the amount that they get back. But it's also the same as if you take out a loan. They're not just going to say, if you take out $1,000 loan, they're not going to say, just give us back $1,000, whatever. It's no big deal. You're going to have to pay interest on it. And last time I told you a little lie. I said that banks use simple interest to calculate your stuff. That's not exactly true. I lied, and I'll be honest with you. I straight up lied to you. And so,
Great, thanks.
Yeah, but I did that for a reason. It was a noble lie. I actually don't believe in noble lies, but I want to delineate in your head. That these things are completely different. And so this is what we said, that this would be after n years with some rate, right? Then this is how much you would owe, or this is how much the bank would owe you if that's your original amount. And then you add that. And we used, and this is what we're going to be working with today, is we're going to say, let's suppose the interest rate was 10%, right? And we could say, well, after 1 year, that's how much you'd have. But after 2 years, they would, and I use this word, compound the interest. That after 2 years, they're basically just doing this calculation twice, something like that. But that's not exactly what compound interest is. With compound interest, this doing the same thing over again, right? Like computing your original amount times this amount times this amount. That is what we call compounding. But this isn't how the banks actually calculate compound interest. And so what we've been talking about is simple interest. But banks use compound interest. And let's talk about what that is. So we're going to start off. Let's just see this. So if I asked this question, you invest $0 into an account at 10% interest for 1 year. How much would you have? Well, how much would you have? I'm not going to write it all. How much would you have at the end of the year? Well, this is, we're just basically using this formula, right? We're saying 1 year. Okay, so you're doing that one time. And so that's one. Okay, no problem there. The rate is 10%. We translate that into our decimal 0.1. And we could see, and it's nice, we don't even have to use our calculator. We get 1.1. So 1.1 times as much as you invested, right? So that's what that means right there. And really, and like if we wanted to, I don't want to use numbers here, but for this very first example, we're going to say, so for instance, if it was $1,000 that let's instead of saying invested in the bank, let's say this is how much you owed. This is how much you borrowed from the bank, and how much are you going to have to pay back? Well, this would be that. Okay, so that's 1,000 times 1.1. Well, 1.1 times 1,000 is the same thing as moving the decimal place over 3 times. So you would owe $1,100 or $1,100. So instead of invest, I guess we're saying you borrow P0. So you borrow $1,000 from a bank at 10% interest for 1 year, or after 1 year, how much would you owe? Well, that would be how much you would owe if the bank uses simple interest. But the bank doesn't use simple interest. It uses something called compound interest. And this is how they calculate this. So first off, we have to have some idea of the number of compoundings, how many times they're going to compound this interest over and over again. And there are a bunch of different ways that this could be said. We're going to start with an easy one. We're going to say quarterly. So if a bank says, so for instance, here's the prompt to the question. You invest P0 at 10%, or rather, no, I don't want to say invest. You borrow. Let's borrow. Maybe this is a car loan or something. You borrow P0 at 10% interest compounded quarterly. How much would you owe after 1 year? That's the question. Well, this is how banks actually compute stuff, is they say, okay, we're going to compound this interest basically. So if it's quarterly, how many times a year will it be compounded? If it's compounded once every quarter, it's a total number of how many?
4.
Yes, straightforward, right? 4 quarters in a whole, and so it'll be computed 4 times. But this is something they do not do. So what they don't do is simply say, okay, we have your original amount that you did, and we're just going to take this 4 times. That is not what they do. They're not. So again, this is not what they're doing. They're not saying, we'll just compute that 4 times over and over. That's not what they're doing. What they do is they say, we're going to break this up into actually 4 things, but it's not the full amount that you owe. They're going to say, let's break that rate also into quarters. And so for 1 year, instead of just saying whatever your original amount is times this one thing, they're going to say, we're going to do it 4 times, but it's not going to be the full 10% that you owe. It's going to be it's only going to be a quarter of it. And so they take whatever that amount is, 0.1, and divide that amount by 4. Which we could figure out which we could figure out if we were so inclined, but that's not really the idea what this is exactly. But that is what they do. They say, okay, you won't owe the full 10% interest each time. It's going to be, since we're compounding 4 times, it'll just be a quarter of that amount. So if it were 10%, they say, we'll compute it, we'll compound it 4 times, but we'll cut you a break, and instead of doing the full 10%, we'll just do a quarter of that 10%. So 0.025 or whatever it would be, right? That's what that number would be. But here's the thing, and this is a really ugly way of trying to write this down. It would be, we could rewrite this as, well, that's just 1 plus 0.10 over 4 multiplied by itself a total of 4 times, right there. And so now what I'm going to do, and I'm going to do this on my calculator. I think you should also do it, Simon. Get off the table. Get off the table. You are not allowed on the table. Get down. Get down. Thank you. No, you can't get up there. I'm sorry. You are not allowed on the table. Come here. Almost. Thank you. Oh boy. So let's compute this number right here. So I'm going to plug this into my calculator. I'm going to do that right now. Pull up my calculator here. Okay, now. So I'm trying to find out what this amount is, and I'm going to go, okay, parentheses, 1 plus 0.1, the rate, the interest rate, the 10% rate, compounded quarterly means they're going to divide that amount into 4. And then they're going to say, well, let's compute it 4 times. We're going to compound that 4 times. And let's see what we get. So that's 1 point. So that is, I'm just going to rewrite this here, and then we're going to drop that in a second. That is 1.10381. We'll stop right there. 1, 0, 3, 8, 1. Okay, so let's get back to the board here. There we go. So, okay. So, okay, you borrow P0. How much would you owe after 1 year? Well, however much you borrowed times that amount. So if it were like last time $1,000, instead of owing just $1,100, you would owe 1,000 times 1.10381. 1,000 brings that over 1, 2, 3 places, and you have $1,103.81 that you would owe. And you're like, well, that's not that bad, really. Like, but you notice it is more, isn't it? Like, it's not as simple as saying, well, we're just going to compound this once, or we're not going to compound it. It's just simple interest, right? If it were just simple interest, it's just an extra 10% of whatever you had. 10% of 1,000 is 100. And so instead of owing the bank $1,000, you owe them 1,100. This is a nifty little way that they could shave a little more out of your pocketbook by saying, well, we'll compound the interest. It's not simple. It's not just one calculation. We're going to do, since it's quarterly, 4. We're going to do this 4 times, and we'll cut you a little break. We'll cut the rate down by a factor of 4, but it's going to result in, actually, I guess it's $3.81 more than had it been just regular old simple interest. Now, that's one way a bank could compound something is quarterly. Another way, I want to leave this up here. So this is, I'm going to leave that initial calculation, which was simple interest at 10%. This is compound interest at 10%, compounded quarterly. And remember how we did that? We said, well, how many times would that be in 1 year? Well, 4 times. And so we said we take the rate, divide it by 4, and then raise it to the 4th power. So here's my question to you. I want a similar one, but instead of compounded quarterly, let's do it 10% compounded monthly. What do I need to write down? And so in other words, I'm trying to get the same little formula here, the same P0 plus some stuff raised to some stuff. When it was quarterly, we did it 4 times, and that's to find the amount that you'd owe after 1 year. If we do it monthly, how is that going to change?
You'd have 1 plus 0.1 divided by 12.
Yes, raised to the
12th power.
The 12th power. And that's exactly what compound interest is. They tell you we're going to compound it monthly. That means that, okay, we'll cut down the rate to 12, but we're going to compound, we're going to calculate how much you owe every month. So it comes out to be a total of 12. Now let's figure this out, because this is kind of interesting. We saw that, okay, if you compounded quarterly, you owed, well, so compared to not compounding at all, if you compound quarterly, you owe some more money. I'm willing to bet that the more times you compound this, the more money you're going to owe the bank. So what I would like for you to figure out this number right here. You tell me, you plug that into a calculator, tell me what you get.
1.10471.
Nice. Okay, I'm going to double check that. So we have 1 plus 0.1 divided by 12 raised to the 12th power, and you got, what did you get?
1.10471.
That's what I get. There we go. Okay. And so if the amount we borrowed was $1,000, then we would have 1,000 times that amount, 1.10471 would give me 1,104.71 right there. So this is at 10%. compounded monthly. Okay. Okay. What if it's compounded daily?
Oh gosh.
What number? How is this going to change? We're going to compound this daily. The bank says, we'll give you a rate, 10%. And you're like, hey, that's not bad. It's actually, well, it depends on what you're doing. It might be really bad. But you say, okay, all right. And then they say compounded daily. Now, how does that change my calculation? What do I need to plug in there?
Okay, so you'll have 1 plus 0.1 divided by 365.
There you go. Raised to what power?
The 365th power.
There you go. Now, all right. Let's compute that. Tell me what you get out of that bad boy.
Do you want to round at all or no?
Well, let's hold on to the same number of digits that we've been using. Let's get 1, 2, 3, 4, 5 decimal places.
So do you want to round up for the 5th?
Oh, yes. Oh, the bank is totally going to round up because they want your money. They want that penny. They're going to get that penny, boy. No, okay. So
you'll have 1.10516.
1.10516. There you go. That's what I got too. And then we're going to say, okay, so if it was $1,000 that we borrowed, it would be that 10516. And so our total amount that we would owe would be $1,105.16. Okay. So like, notice that was a pretty big jump, right? Like, we started off with 4, okay, and from not compounding at all, just simple interest, when we jumped up to 4 times, we paid an extra $3.81. Then we jumped from from 4 compoundings up to 12 compoundings. We increased it by a factor of 3, and we only owed an additional $1, really less than $1, because at $3.81 up to $4.71 wasn't that big of a jump, even though we increased the amount of compoundings a total of by a factor of 3, right? From 4 compoundings to 12 compoundings. That's a lot. Then we said, well, let's just go crazy here and compound every day. So we jumped from 12 compoundings to 365 compoundings, and we didn't even really get a full extra $1. We went from 471 to 516. Really wasn't that much. There's something going on here. And what we're about to do right now is going to be arguably one of the most important things in mathematics.
Okay.
So I'm going to throw that out there, right? Like, what we're about to do is going to be very, very important. I'm going to investigate this because something tells me, right? Well, first off, it's pretty obvious that when I put in a bigger number into here, right? Like, we were at 4. Okay, if you make the 4s bigger, like jump it up to 365, obviously the number is getting bigger. Even though we're cutting the rate down by a huge factor. So this number here is getting smaller, right? 0.1 divided by 4 is way bigger than 0.1 divided by 365. So the amount inside is getting smaller, but the amount out here that we're exponentiating by is getting a lot bigger. And so, okay, there's some weird stuff going on. Something's getting smaller, but overall it's getting bigger. And we can see, yes, like the actual amount is getting bigger. And so my intuition is that when you make this thing bigger, it's going to continue to get bigger. And my intuition about that is it should just keep getting bigger forever and forever. And the bigger number I plug in there, it's just going to skyrocket eventually. And then I'm going to owe infinity dollars to the bank, right? But I'd like to investigate this. And that's what we're going to do. And just to make our calculations simple, we're going to pretend that we're calculating some kind of interest rate like this. But to make calculations simple, we're going to say that the rate is 100%. Why? Well, because I don't want to deal with a decimal up there. I'd like to just have an easy number. How about 1, right? And 100% interest would be the number 1, right? Check me on that. If something's, it should just be a 1. Yeah, okay. So let's do that. And so what I'm going to have you do right now, I'll do the first couple of them, but we're going to make a table. And the thing that we're going to do, the value that we're going to compute is that interest rate, or that compounded interest rate. 1 plus, and we're going to take the actual rate to be 100%, just to make calculations easy. We're going to have a nice 1 right there. And then we're going to basically increase the number of compoundings here. That's the thing we're going to compute for different values of n. And I'm going to do the first couple of them with you. And then I'm going to say, get out your calculator and do this, and then get back with me when you're done with all of these. So for instance, and this one we don't even need a calculator, when n is 1, the number we want to compute is going to be 1 plus 1 over 1 raised to the 1. So that's what I would plug into my calculator, only I don't need a calculator for that. 1 divided by 1 is simply 1. So that's 1 plus 1 raised to the 1, which is 2 raised to the 1, which is just 2. So here in the first column, we're going to have 2. Then what I'm going to do is put a decimal place right there. We'll see why in just a second. Here, buddy, you want some almonds? Okay, you got some almonds. Here you go. Come on. Come over here. The almonds right here. Okay. Thank you. Okay, so let's do it with 2. So when n is equal to 2, we get 1 plus 1 over 2 raised to the 2. And I'm going to just use my calculator for that. I could do this. This one's actually not hard. We could do this, but I want to show you what I'm looking for when you go to do the rest of these. I'm going to say, okay, I want to do, when n is 2, I have 1 plus 1 over 2, yes, in parentheses, raised to the power of 2. I hit enter. I get 2.25. Okay, so what I want to do, and this is one thing that I want you to do with this, is line up these decimal places as you go and do these. Just like that. Okay, so do you understand what I'm asking you to do?
Yeah.
Now, here are the numbers I want you to use. So here, so n, the next one I want you to do is 10. Then I want you to do 1,000. Then I would like you to do 10,000. Your calculator should be able to handle all of these that I'm going to write up here. Then I want you to jump to 1 million.
Well, okay.
Then let's go to 100 million. And should we do one more? Yeah, let's do one more. Let's do 10 billion. 10 billion. So the bank says we're going to compound this 10 billion times a year. And you go, oh no, what's going to happen? So let's just see what happens. So 10, 0, 0, 0, 0, 0, 0, 0, 0, 0. So I want these numbers. I'm going to do them too. Please don't look while I'm putting these up on the board, but just yeah, fill out this table. Any questions? You know what I'm asking you to do?
I think I'm good.
Okay, cool. Well, so I'll see you in a few. I chopped off the last one because my calculator couldn't handle 10 billion.
My calculator did it.
Yeah, and it gave you the wrong answer. Trust me on this, it did.
Oh.
Yeah, it actually can't handle it. Something called rounding error, which we don't have time to get into, but it screwed everything up. So, did you get something like this?
Yes.
Yes. Now here's something to notice. Okay. And this is kind of what we saw before. Like at first, when you jump from like simple interest, which would be where you're just compounding once, or you're not compounding at all, you have some amount. In this case, it's 2, which makes sense. If you're paying 100% interest, then you're going to owe twice as much, 2 times whatever you started with. Compounding bi-yearly, or in other words, compounding twice, jumps up by a lot relatively, right? You jump up to an extra 0.25. Then, and this is what we saw before, but then you make a big jump and it doesn't jump up as much, right? We're only paying an extra, I don't know. I mean, that's close to 25, that's close to 30 cents on the dollar. Then you jump up from 10 to 1,000. We've increased it by a factor of 2, right? We've multiplied that by 100 times more. And so, yeah, I guess we've increased it by a factor of 100, and we only owe an extra 22 cents on the dollar. Then you do that again, right? We're going to jump up by another factor of 100. And now it's not even changing that much. We're owing less than a penny. We're owing 0.02 of a penny extra. Jump up again by a factor of 100. And now we're agreeing down to here, we're only off by 1,000th of a penny. Jump up again. Now we're up here at 100 million. And we agree all the way down to here, right? So what we're seeing, what's happening is that one way of thinking about this is we have a sequence of numbers, right? A bunch of numbers in succession, and they're getting closer and closer to some specific value. What I want to do real quick is show you what this looks like on a graph, because I like to think in terms of graphs. So let me share this with you. Okay. So share that. Okay. So can you see this?
Yes.
Okay. So let's see what's happening. Don't worry about the stuff on the left-hand side. It looks kind of complicated, but all I've done here is I've said, if you look down here, you see the 1, which means, okay, when n is 1, and we saw, then yes, 1 plus 1 over 1 to the 1 is 2. We plugged in a 2. We said 1 plus 1 over 2, take that to the second power, and we get 2.25. And I don't have all these other ones in here. I didn't compute 3 and 4. But you see what's happening. It's increasing with every time n increases, the value of the thing gets a little bit bigger. And I'm going to zoom out just a little bit. There's 10. We did 10, and we got 2.594. It's just rounding a little early. That's exactly what we got. And every time the amount that it's going up, right, we're taking the same step over to the right, right? We're adding 1 every time, but the amount that it's increasing with every step is getting smaller and smaller. And if we zoom way out, we could see that eventually, like, it's not getting any higher at all. Here I've only plotted to 100, and we already did 100, and we got 7. Oh, we didn't do 100, we did 1,000. But at any rate, this is the idea. This is, and we've kind of seen this before. This is, if we think about this thing as a function, which here I'm going to basically say, well, instead of plugging in integer values, what happens if we plugged in 1/2 or 5 2/7? What we would have is this thing right here. We're just kind of connecting all the dots. And we've seen this before. Here, I'm going to get out of this and just kind of get on the board now. we've seen this before, and we've called this type of thing an asymptote, right? Where we had something like this, like 1 over x, and the values approach, in this case, 0, but they never actually get there, right? This type of thing, what we're doing right now is we have a sequence that's approaching some value. It's getting closer and closer and closer to some value right here. And the idea is, contrary to my expectation, which was, well, if you plug in a bigger number, you'll get out a bigger number. And eventually it's just going to blow up and you'll owe the bank infinity dollars, right? That's not what's happening here. This is approaching a specific value. And we could formalize this by saying, if you continued this process out to infinity, if you were somehow able to plug in infinity or whatever, then the value you would get out is the number e. The value that this sequence is approaching is, we define it to be the number e, which is approximately 2.718281828459045, blah, 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 blah. Goes on forever and ever, just like pi. It never repeats. It never, you say it repeats right here, 18281828. Yeah, but then it doesn't keep doing that forever. It's an irrational number. And it's arguably the most important number in mathematics, or it is as important as 0 and 1. Every bit as important as 0 and 1. It is fundamental. It is kind of beneath everything in math. Everything. It's crazy. It shows up in crazy places. And yeah, and so this is a very important idea. This idea that, this is what I was saying, like, what I'm about to show you, what we're about to do, is one of the most important things that you could take from a math class. And it's this idea of convergence, that we have some sequence of numbers and they don't just jump off to infinity, right? Like, we're plugging in bigger and bigger numbers. We're raising some number to a big power. Well, and you think, well, if I plug in infinity, I'm taking a number and raising it to an infinite power, it should give me back infinity. No, it won't. It actually gives you a number. And that's what we mean by this is, and I like this as a visual, right? This is what we mean by convergence. We say that this sequence converges to some value. That value is e. In fact, and this is going to look crazy, but this is how it's said in math, is that the limit, and we write LIM, the limit, as n goes to infinity of what? Well, of this sequence right here, this sequence. So as I plug in bigger and bigger numbers into n, it actually doesn't blow up. It doesn't go off to infinity. It converges to some value. So this limit actually exists. It's not unbounded. It doesn't go off forever. It approaches some specific value, and that specific value is what we define as, right, the 3 bars. I'm saying this thing right here is defined to be the number e, the most important number in math. So this looks a little crazy. I'm sorry, but when you take calculus, if and when you take calculus, this is the first thing you're going to learn is limits of stuff. Not necessarily this will come later, but you're going to learn that a limit is this idea. Like, you keep going on and doing this and pretend you could do it out to infinity. What would you get? Would your thing blow up? Turns out in this case, no, it doesn't. It approaches some value. That value is very, 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 very important. So important that we give it a name. That name is E. Now, it turns out now, and you're like, what does that have to do with 100% interest? Well, this is one way, and this is how I like to do it. This is how it was taught to me. The first idea of a sequence that converges to a value. And so I like to do it that way. But E itself is not it's not defined really this way, or rather it doesn't come from computing compound interest. This is just one way we could get to this number. There are a bunch of different ways of arriving at this number. Like I said, this number E is fundamental. It is beneath pretty much all of mathematics that we do. And so there are a bunch of different ways of arriving at this number. This is one of the ways. And we could, so much so that we could define this number this way. That's like I did with those 3 bars right there. I'm saying we could define this number this way. So, okay, what does that do for us? Why are we learning about this thing now? Okay, well, here we go. So any questions about this table and all of this stuff right now?
I don't think so.
Okay. So basically everything that we've done right now was just to introduce this number because your book says there's this number E and it's approximately 2.7181 and that's it. And then it says it's really important, but I hate that they don't tell you. And like we just did stuff about compound interest. And they don't go. There is a problem in the book that kind of suggests this, but I think it's really good to know that this is true. This is a thing. This is a big thing, this idea. So what are we going to do with this? Well, one more little fact that we need, and this one is wicked hard to prove, because you might be thinking, when are you ever going to pay 100% interest on anything, right? And you're not, hopefully you won't. So what good does this do? Well, this is the thing about this, is that let's think back to just the formula I'd written down for compound interest. I had something like this. I had 1 plus the rate. I don't think I ever actually wrote this down. That's the formula for compound interest for where N is the number of compoundings per year, and R is the rate, just like we had before, right? It's usually a decimal, something between 0 and 1. It turns out that we could have done this if we wanted to. We could have said, okay, instead of using a 1 here, like we did when we computed that table, we could have picked anything. We could have picked, let's say, 1 plus 0.1 over N and computed this table. And what I want to do right now is, like we saw that when N got really, really big, we got really, really close to this number. So what I'm going to do right now is just do one of those computations. I'm going to say, let's have you do it too. So let's compute, let's say that the 1% and the number of compoundings was 1 million. And so you plug that in and tell me what you get. I'm going to do the same. 10%.
Okay.
Okay, what'd you get?
1.105117.
Yeah, we'll chop it up right there. 1 7. That's what I got too. Okay. So now here's the interesting thing is, uh-oh, I lost you. Where did you go?
I'm here.
I see you. So it turns out that this right here now, and again, right, we had to stop short because our calculator doesn't know how to plug in infinity, and around 10 billion, it doesn't work anymore. So it turns out that if we had done this same thing and continued on forever, in other words, I'm saying if we were somehow able to plug in infinity, And instead of having a 1 right there, if we had our R right there. And so I'm saying if we continued this same process on and on and on and on for infinity, the number that we would get out is the same thing as E raised to the power of R. This is wicked hard to prove, actually. Like, that's a toughie to show that that is actually true. But I want to try to convince you that that's true by just doing a couple calculations. So we've already done it here, right? We said, yeah, I could see that if we kept doing this, by this point, if we plugged in a bigger number, we shouldn't get anything much different, right? We saw that before. By the time we got to 1 million, we had a good 5 decimal places that were stable, right? So what I'm going to do right now is just see if indeed, I'm going to see what happens when I take E. And what does this say? Whatever the rate is, if I just take E and raise it to that power, I should get something very close to that. So I'm going to take E and raise it to the power of 0.1. I want to show you how to do that on a TI 84. Is that what I have? Yes, TI 84. Here we go. Okay, so this should look a little familiar. I go and find, where's the E key? It's down here with natural log.
Oh no.
That's that guy right there. And so little e raised to the x. And so I'm going to do that by hitting, and it's in blue. So I know, okay, I hit the blue second key, go down and hit this button, and it gives me E. And if I raise that to the 0.1, let's see what happens. I'm going to E raised to the 0.1 gives me, that's really close there. I was not expecting it to be that close. 1.1051709109118. And the previous one was 709126. So you can see that, hey, these two values agree very closely right there. So this should convince, or at least suggest to you, that this isn't just hogwash, that there's something to this. And it is true that if I had taken a bigger number here, just like before, this would have given me an even closer approximation to this guy right there. Do you buy that? Do you understand what I'm saying with that?
Yes.
Okay. So we have this nifty fact, and this is how we can compute. And on one hand, this is useful because this lets us compute interest compounded continuously. In other words, we're going to do an infinite number of compoundings in, let's say, like a year, instead of 4 compoundings a year or 12 or 365. If the bank says we're going to do this infinitely many times, well, it doesn't shoot off to infinity. It's actually not that bad, but that's one nifty way that we could do this. And when we go to on Wednesday, we'll actually go into applications of this kind of stuff. We're going to be using that extensively to compute compound interest compounded continuously, which some places will do. And so that's nice. Okay, that is what you would have right there. We'll review that in a second, but what's even way cooler than that is, like I said, this thing shows up not just like in math, but in nature itself. And this nifty little function right here, and if we imagine, I'm going to get rid of this stuff because we're done with this. If we imagine that, like, this is like compound interest here, so this is some kind of growth going on. And if we imagine that this thing, we have the limit of this thing, whatever it is, and it comes out to, say, e to the r, whatever that is. And then if we take that as a function of time, like that's my amount. So like we had before. You have some amount here with simple interest. It was your rate. And then we've been using, I told you we're going to use n last time because we're thinking about it's a discrete process and it rolls over once every year. But if we say, well, what if you wanted to take your money out of the bank like halfway through the year? If we had some kind of, not a discrete variable, but an actual t, right? So after 45 days and 700 seconds, well, I could compute that and raise that to that power. It's the same kind of thing right here. We could say, well, that's the rate that the bank is giving you. And you can just take that rate and raise it to some time. That's basically the idea of what we did before. Only I said we had to use integers. Now we're saying you could use any number at all. It doesn't have to be an integer. This type of thing shows up in the world all the time. And real quick, I'm just going to use my properties of exponents. It just says, like, if you have e to the r and then you raise that number to the t, it's the same thing as e to the r times t. It's way easier to deal with stuff like this. It turns out that very many things in the world have this relationship. For instance, population. If you have, like, almost all populations are modeled with this thing right here. For some rate, we don't know what rate necessarily, and oftentimes we want to find out. But if you have some population of, let's say, people in a country, it almost always obeys something like this. You could find the total number of people in your country after a certain amount of time has passed, given an initial population. This thing looks something like this, because it's an exponential function. It goes through here at p0. Y, plug in a 0 for t, right? P of 0 is p0 e to the r times 0. That's the same thing as p0 e to the 0. Anything raised to the 0 is equal to 1. And so that's your initial population right there. And then after some amount of time, t, you want to know how big should my population be in, say, the state of Washington after 25 years? You'll plug in a 25 and we could get a pretty good estimate of what my population should be. Bacteria, stuff like that. You know, how many bacteria do I have in a culture? This type of thing is good. There's also, this is called, so we're almost done. I just want to give you a broad overview of the ways we're going to use this bad boy right here. One is interest. One is this type of thing, which is called exponential growth. But also, what if the population isn't growing? What if it's shrinking? What if it's doing something like that? Well, it's the same idea, only instead of a positive number right here, you have a negative number. And this would be something like this. P of t equals p0. And so there's your p0 times e to the, and we're going to give it a different number. How about k? E to the negative kt. And this should look, you should be able to intuit this, because, like, for instance, 2, e is very close to 2. It's 2.7, but whatever. 2 to the x shoots up like this. 2 to the negative x comes down like this. These things pretty much have the same shape as 2 to the x. But here, with k being a positive number, negative k would be like negative 5 times t, would make this thing come down, and it gets smaller and smaller. This type of thing is called exponential decay. And another, so not just populations that are declining, but also, and this is, we're going to go into this in detail. We're going to do a bunch of examples of this on Wednesday, but also radioactive decay is exponential decay. So if you have a radioactive isotope like uranium, certain isotopes of uranium spontaneously decay. And if you want to know, say I have 10 grams of uranium, and I want to know how much uranium am I going to have after 15 days, we could figure that kind of stuff out and figure out, okay, after 15 days, you should have, I don't know, 7.3 grams of uranium left. So E is everywhere, and it's super important, and not just for like a couple of reasons that I gave. I can't even begin to tell you how fundamental and how important this number is right here. If there's one thing you take from this class, if there's only one thing you take from this class, this right here, and what it means, right? Not just the symbols, LIMN, arrow, infinity symbol, blah, 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 is defined as E. Like, if you remember what that means, how we got that, you keep plugging in bigger and bigger numbers and it gets closer and closer to some value. That value is what we define to be the number E. That's all you really, well, it's not all you need to take from this class, but if you choose to take only one thing from this class, please take that. That is, it's so important. So that's it. There's one more thing I wanted to do. We have 2 minutes, and so I will just real quick, I'm going to go back to the calculator here and just show you. So I took E and raised it to 0.1 and got something out. If I wanted to actually know what is E, right? And we said it was getting closer and closer to 2.78 some stuff. Well, wait a second. What is 2 to the first power? 2 to the 1 equals what?
2.
3 to the 1 equals what?
3.
So E to the 1 equals what?
E.
E, right? So I'm going to compute that. I'm going to tell my calculator, okay, take E, raise it to the first power, and it should tell me what E is. Sure enough, indeed, there's that. That's the number. It's been chopped off. They chopped it off early because my calculator can only do so many, but that's the number right there. It's some value. So when we go to do and deal with these things, remember E, yes, it is some magical thing with this crazy formula, but at the same time, it's just a number. It's just roughly equal to 2.71828, blah, 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 blah. And so it's some number between 2 and 3. And all we're doing is we're taking that number and raising it to a power. That's going to be the name of the game for a long time. So that's it. I'm going to give you one question for homework, and it's from page 556, and it's pretty much what we just did. Page 556. Page 556, number 39. The very last part, the very last thing says, what can you conclude from this result? That's what it's getting at. And the way it's written, without any kind of explanation of anything, you probably wouldn't have got it. But like, that's what we're getting at, is that there's a limit going on. There's that the bigger numbers you put in, it doesn't go off to infinity. It approaches some value. That's the value. So I hope this was, I hope you had a great time. Welcome to the world of deeper mathematics.
I mean, I thought it was interesting.
Isn't it? Like, this is one of the things that really got me interested in math. I was like, because I just think, well, bigger numbers, it's just going to get bigger. Obviously. No, something interesting happens. And it's pretty cool.